And so, hello everybody. In the last video, we are just chugging through our Navier stokes again. So, this video, we're going to continue the simplification of the Navier stokes equations. So, we have derived something of this sort already. Alright, it's somewhat neat-ish, so we just want to trim it down. Okay, so we have already derived our forces due to stresses, forces due to body forces like gravity, and now we have also considered the effect of these forces. So it's the rate of change of momentum in the control volume, or box as we like to call it, and also the effect of the moment. It causes, like, momentum to exit and leave the control volume of our interest. So we want to simplify things, firstly by dividing by the volume, delta x, delta y, delta z. And of course, we want to factorize this delta x, delta y, delta z out, and seeing how it's constant with respect to time, we can just take it out of the derivative. And now we want to divide everything all the way through. So that's the reason okay, so let's tidy up. Okay, so 1, 2, 3, 4, 5, 6. So we divide throughout first. And now, of course, we want to limit delta x, delta y, delta z goes to 0. Alright, so what does this value become? This one just becomes partial with respect to z, tau zx. Okay, this one becomes a partial with respect to x, sigma xx. And likewise, this one is a partial with respect to y. Okay, partial with respect to y, tau, acting on the y plane with respect to the x direction. Alright, so you see that these letters are the same here. The first letter and this letter are the same. So we'll do the same for the right hand side. Here is the partial with respect to x, rho u dot u. Now this is a partial with respect to y, rho v dot u. And this is a partial with respect to z, rho w dot u. Okay, so now we want to consider collapsing these. Of course, we can put it this way. If you notice, this is actually the divergence. Alright, this looks something like a divergence, but you see, inside it's kind of different. It's not like our mass balance. Okay, it looks at our mass balance. Okay, we will need to do something. Okay, it looks a bit like our mass balance. So let's copy our divergence over. Alright, let's copy our divergence over, and we see what divergence is actually looking like. So the u is kind of the same throughout everything. So rho u, rho u can be factorized out, so to speak. Okay, so we want to replace by divergence. dot row u dot v. Okay, so what are we doing? We want this, right? We want the row u, the row v, and the row w times u. But I see we can factorize out, so to speak, row u, right? Okay. So if we factorize, okay, so this is mass, and this is the momentum. Okay, so let's see. So we have a row u. No. Oopsie. Okay, and a row u dot v, a row u dot w. We'll have this simple divergence here, right? Alright, so now our Navier-Stokes equation is very much trimmed down, but let's trim it down even further. There are some more things that we can do. Okay, let's trim it down further. Now we note with our divergence operator, we can apply the chain rule to it as well, or the product rule to it, because it's essentially a differential operator. Okay, so what are we going to do? Okay, we have to, we kind of want to yeah, we want to so-called factorize things out. Okay, so let's do it this way, or rather, okay, so, never mind, so that things become clearer, we'll use this form first. Okay, we want to apply the chain product rule for all these, because there's a way we can trim it down even more. So let's have two x derivatives, row u plus u plus, oh, take a look at this, row v y u plus the last one. So I'm just applying the chain rule, product rule, sorry. So this side is constant, differentiate the other side, then the other side becomes constant, and differentiate this side. So I'm going to do the same for all three. So it's going to get a little messy, but don't worry. You'll see why I'm doing it, so that we can, the idea is we want to trim down this Navier-Stokes equation even more. So u partial z row w. Okay, now I want us to notice a pattern. Can we see that these terms, okay, what are these terms? 1, 2, 3, right? Okay, I show you again. 1, 2, 3. Now, all these have in common this u in front of them. Okay, so I'm just going to write it this way. I'm going to factorize that u out. Okay, so 1, 2, 3. So I'm going to get rid of the u's that are left behind. I'm going to put all of this to one side. Okay. Alright, so there we have it. Okay. Now, we are going to put this back into our Navier-Stokes equation. And then we are going to also differentiate this total derivative. This partial derivative, sorry. So, let's highlight it just to ensure we are clear what we are doing. This is 1. This I shall use a different color. This is 2. Blue is a bad color. Let's use green instead. So this is green. Okay. So I'm separating out the two derivatives. So rho u partial t plus u partial rho u. Okay, I'm just applying product rule. Okay, so I'm gonna put all these here, and now with the highlights it should be slightly easier to see. Okay, let's do it this way. I'm gonna highlight this in yellow. I'm gonna highlight this in green. Tup, tup, tup. 1, 2, 3. There you go. Now, can we notice that this thing also has a u inside of it? So I'm just gonna copy this over. Copy this over. And I'm gonna get rid of this. Now, can we take a look at this equation? Does this look very familiar to us? Now, let's take a look at our mass balance. So we're going to combine our mass balance into the Navier-Stokes equation. So, what's our mass balance look like? Our mass balance looks like this. I'm going to bring this down here. This is what our mass balance looks like. And I'm going to change this into a divergence form. Okay. And now look at what is this. Ah, yes. Beautiful math, it turns out to be 0. So this term can be completely cancelled. That's a beautiful thing here. So we can just delete this off. Substituting mass balance into the momentum balance, we will get this equation. So yes, there is some, although Navier-Stokes is mostly the concept is behind it is a force balance. Let me spell that right. While the concept is definitely a force balance concept, we have actually substituted the mass balance in to get this term. Now, I want to introduce a new operator. Can we take a look at inside? And we notice that all these derivatives, they're actually talking about u. Alright? And of course, if we factorize that density out, we'll see a pattern emerging. All of these are actually talking about the same thing, u. I want to introduce this thing called the substantial derivative. This is another way that people like to collapse things. So some people call it the total derivative, depends on the textbook you are looking at. Okay, so introducing the substantial Okay, now if you look online, substantial derivative, now this is actually known as the material derivative on in Wikipedia. So again, take a look at this. It's called advective, convective, derivative, blah 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 blah. It's even called a Lagrangian. So this is what it actually looks like. Remember our divergence operator that we've introduced a few videos back. So you can see that there's a divergence operator here, del x, del y, del z. Okay. So plus, so the v vector dot, now blah. All right. So it's or rather we can just leave it like that. So we have a v vector and we are have a dot product with something. Okay, so this is what our substantial derivative is. You can just remember this: t, u in the x direction, x velocity differentiate with respect to x direction, y velocity differentiate with respect to y direction, z velocity differentiate with respect to z direction. So now it will make the Navier-Stokes much easier to remember. So we can just replace the entire right hand side with this, as long as remember what this substantial derivative is: u. So I'll just highlight this in yellow. So we have converted this whole thing into this. So this is the x direction momentum balance. Now there is actually one last part, because we have not actually considered these forces that are acting on the body that we are talking about. So we are going to do that in the next video. I'll see you guys next time. Thanks for watching. Bye bye.